having some solar and some gas. Okay? So let's start.
Good morning, everyone. Okay, so, well, I'm Damià Gomila. Okay, I'm a researcher here at IFISC. And I'll explain you today, it'll be something simple. I hope you'll enjoy, nothing complicated. Is a research line we are carrying out here in, is Eder Batista, who's sitting over there. He's a PhD student. He's done the main work here. And then Piero Coletti is also involved in this research line. So I'm going to talk about the dynamics of the power grid. And in particular, I'll explain how to reduce fluctuations in the power grid using smart devices. I'll make a large introduction so you can you can get a flavor of what we do. Okay. So the first thing is, just for those of you that don't know, I'll introduce how the electric system works. Okay. And then in particular, we need a model for that. So I'll explain the model for the power plants, and then a model for the electrical demand, which will be a stochastic. I'll explain briefly. And afterwards, the main topic, what we do, the research we do, is introduce demand-side management. I'll explain what that is later. And then I will conclude. Okay, so first, general introduction of the power grid system, or the electric system. Well, of course, is one of the most important infrastructures we have. Okay, but together with the transportation system and I don't know, sanitation or something like that, and agriculture probably maybe, and electricity is everywhere. No? So this is a huge and very important infrastructure. Essentially, it has four stages. Has the generation of electricity from a primary source. Then there is the transmission of the electricity from the generation to the end point, and this is divided in two: the transmission, which is the high voltage power lines, high voltage network, and then is the low voltage network, which is called distribution. So it's transmission and distribution that reaches to every house. And then what is us, which is the consumers, where the electricity is consumed. And of course, consumer and generation are linked in the sense that nowadays there is no storage of electricity, or there is no storage in a massive amount of storage. So the key point here is that at every moment in time, generation has to be equal to the consumption. Okay, otherwise you have a problem. And that's the key point here in the control of the power grid. Well, this is a picture, a cartoon of what this is. So these are the big power plants, coal or whatever, hydroelectric. And then this is wind farm. Then this is the transmission, so the high voltage power lines. Here in Spain, I think is in every country, this belongs to a single company, which typically is publicly controlled, or at least has public participation. In Spain, it's called Red Electric, because this is a critical infrastructure of the country. So it has to be, it's a monopoly. So it's a single company that deals with the transmission. And then you have the distribution that's in private companies already. And then these are the consumers. As a matter of fact, the power line, the power system, the power grid is the largest machine ever built by a human. In extension, in kilometers. So this actually extends, let's say you can consider whole Europe or the whole North America as a single, as a single device, or a single machine. Yeah. Okay, so that's like it. And as a matter of fact, it's more complex than that. I just did it like that because the power grid is actually a multi-layer network. So you have, I already mentioned two, so that's the transmission line and the distribution line. These are really two power networks, okay, at different, these are two complex networks at different levels. And not only that, you have many other stages. You have communication networks also, because you have to synchronize all the power plants, things like that. And this is, there is a lot of technical intermediate steps in the middle, so these are several layers. There is also a market operator. So you have to come up with a price for the electricity, and there is a market there also. So there are different levels of interaction between, let's say, producers and users. For what generation in Spain, like the problem As an example, simply here there are 55 large thermal power stations, 8 nuclear plants. These are, let's say, plants of 1 gigawatt or more, or close to a gigawatt, and 20 hydroelectric power plants over 200 megawatts, 22 wind farms, and so on. So it's a large, pretty large infrastructure. And at the consumer side, we have 22 million users that consume in average 10 kilowatts hour per day, okay, per family. This amount, the cost for the users is €2 per day, more or less, in average. So it's a huge infrastructure in terms of, let's say, machine, and also in terms of economy, from the economic point of view. So the question I pose to you is now, this thing is certainly huge. Now, is this a complex system? You think the power grid could be, so if we are studying here, not this school, and probably you are interested in this. So is this a complex system? What do you think? Any guess? Well, it's certainly complicated, okay? So this is the control center of Red Eléctrica in Madrid. No? It's a huge thing to control, to coordinate everything, and so on. No? So it's certainly complicated. But one could argue whether this is or not a complex system. In particular, well, for the power plants, it has some characteristics of a complex system. That you have 65 thermal power stations and 8 nuclear power plants, and all these are synchronized in a network. Okay, so there are some synchronization issues and cascading effects that are related with complex systems. Okay, so from that side, there are works that study that. Okay, from the point of view of the consumers that we are interested in, as a socio-technical system, okay, these 22 million consumers, from that side, this is not a complex system, in the sense that you have many users, but they do not interact at all. So there is no interaction. Interaction is one of the key issues of a complex system, okay, to have emergent behavior. So as it is now, the electric system, the power grid, is not a complex system. It means that when you go home, you switch on devices on and off, and you don't care what the others do, okay? So there is no emergent behaviors of any type in principle like that, okay? There are some things like at a football match, everybody gets to, these kind of things. Through other channels, you may have emergent social behavior, okay? But not the power grid itself. And I've been saying that because later I will introduce this interaction that makes this system complex. No? I will say, I'll argue that this is something that we have to deal with in the next years or in the future. Okay, so that's the system, and well, we try to model it to study this thing. And well, we have to model the generation, we have to model the consumers, and then we put all together and see what the behavior, what behavior emerge. So first, the model of a power plant, and it may look like a complicated thing to model. No, power plant is a huge thing, very complicated. But you'll see that in the end, it's very easy. Actually, it's very simple. There are several model plants to model, and you may have to, model one, each one in different ways, but in principle, you can approach them in the same way. This is a big hydro power plant. This would be a coal, wind farm, or solar farm. Essentially, all do the same. They take a primary source of energy. In this case here, that would be a coal plant. Okay, so that's a primary source that you somehow use. In this case, you have to burn, and you generate a steam at high pressure, and this steam at high pressure makes rotate a machine, okay, a turbine, and this rotate, and this is essentially what the steam drives the blades, and the blades drive a generator that produce alternating current. Simply like that. It is instead of coal is wind. The wind makes directly rotate through the blades, makes directly rotate the turbine. In the case of solar panels, you don't have this. The photoelectric effect converts solar energy directly into electricity. Okay, so there are some differences, but in general, when I model here, I have in mind something like this: primary source of energy that makes rotate something. Okay, and then you generate electricity, which is feed into the transmission lines. In principle, you have a lot of electromagnetism involved here. Okay. But I'll see that this is actually not essential for what follows. But so essentially how it works, so the basic physics is the Faraday law of induction. So what you have is a big magnet, or you have a magnetic field, and you have a coil in the middle that you make it rotate. Okay? When you rotate the coil, the magnetic flux, you have the magnetic flux, which is the integral of the electric field through the surface of the coil. This evolves in time, so this rotates, okay, and it generates an electric field. If an electric field, an electric current. So if the coil is closed, you have an electric current. If it is open, you have a voltage difference. And the voltage difference, if this rotates at constant speed, this is just an alternating current that goes as the sinus of the frequency time. And that's it. Essentially, you have this alternating current, and then you have a resistance. That's the relation between the intensity and the voltage. You have capacitors or a coil that has induction, so you have an inductive reactance, and so on. Okay, I'll not go into details of that. Okay. So in principle, there is this electromagnetism, but I'll not deal with that. So I'll not talk anymore about the electromagnetism in the rest of the talk. No? So I'm more concerned about the torque. So what happens here is that if you have, as I said, you have a magnetic field and you have a coil rotating. You remember this from your basic physics course, no? So you have a magnetic field and you have a current in this magnetic field. You have a force acting on the current, okay, that goes upward. Okay, so if you have here a magnetic dipole, essentially, in a magnetic field you get a torque. So you have electric current in the coil. This tends to rotate. This makes it to rotate. Okay. And so this is from the electric point of view. So since here we have, you have the current is essentially the area of the coil times the intensity. That's the magnetic dipole. Okay, and the intensity is an alternating current, given the resistance of the circuit. Okay, so this is let's say the torque that happens of the electric. So the torque on the coil because of the electric current going through. Okay. So this means that you think of the power plant, which is rotating and generating electric current. When you switch on a light and you let some current going through the coils, okay, this is creating a torque at the power plant, okay, and is breaking the power plant. Okay, so it's forces what is going on here. Okay, and essentially you want if you want the voltage fix and the frequency fix, the machine has to produce a mechanical torque that has to be equal to the electric torque, to the torque provoked by the electricity. And that's the issue, essentially. A power plant, what it does is it generates a mechanical torque to compensate for the electrical torque in the coils of the generator. And that's everything that I'll talk today, essentially. Okay, so this is the torque, and then we'll model the plant using what is called the swing equation. The swing equation tells us just that. This is the second derivative of the angle of the coil in the magnetic field. Okay, so this is the angular acceleration. This is the moment of inertia of the power plant. Okay, and this is the Newton law. The force is equal to the acceleration in a rotating machine. So we have here the mechanical torque minus the electrical torque. This is the net torque in the power plant. Is the acceleration of the phase. That's it. So there's Newton's law. So we're modeling a huge power plant, very complicated if you like, with the second Newton law. So that's how is it. And then this is the frequency, is the first derivative of the phase. And if we multiply this equation, it's okay. Yeah. If you multiply this equation by the frequency, then instead of the torque times the frequency is the power. Okay, so that's the force divided by time. That's the power so you can write this equation, the swing equation, in terms of, instead of the torque, in terms of the power. And then, just make some conversion. This is the kinetic energy of the power plant, of the rotor, which is rotating, and we define the h, which is the inertia constant of the machine, in units of the, let's say, the nominal power of the power plant. Okay. Then with this thing, we write this equation, which is the final one, which is the swing equation, which is the derivation of the frequency. So the angular acceleration is proportional with this. Well, there is a frequency here. It's proportional to the difference in the mechanical and the electrical power. Okay? What this means? This means that if you have some consumption, electrical current, if you are generating more power than which is consumed, okay, the frequency will increase. Okay? So the system gets accelerated and the electrical frequency increases. And vice versa, if you are consuming more more electrical power than mechanical power is the power plant is generating, then this is negative and the frequency decreases. Okay? And that's it. So that's how it works. So what happens is that precisely you want the system to work precisely at a constant frequency. In Europe is 50 hertz. So that's the frequency of the electrical current. So you want to keep, the system has to be operating at 50 hertz. But the demand, of course, is, fluctuating, okay? Because we switch on devices all the time, the whole population as a whole. So you have to tweak constantly the mechanical power to keep the frequency constant. And that's the tricky point, okay? That's the tricky point. And this is what the system operator does. That's what the power plants do, okay? So in addition to the swing equation, and this is the mechanical power, we need to put a control in an automatic control in the mechanical power to compensate the frequency deviations. Okay? And this is what is called, what the speed drop governor does. It's a control, so we have here an equation for the mechanical power. Okay? And essentially this what it does is, I'll say it properly, I think this is a proportional control. And essentially what this does is, if at a certain point the electrical power is larger than the mechanical power, the frequency drops. Okay? So if the frequency drops, this is negative. Okay? And with this minus sign here, this is positive. So the mechanical power has to increase. So essentially the power plant, if the frequency goes down, automatically accelerates and give more mechanical power to compensate for that. And what the speed governor does first is that if the frequency goes down, it stops it from going down. Okay? And that's why it's called drop governor. It stops it from going down. And this is called primary control. So essentially, it's like a damping. If the frequency deviates very fast, it avoids, goes against the deviation from the reference frequency. And then, since you want to be back at 50 hertz, we have also the secondary control, which is the second equation here. Okay, there was a constant here, PS. It was constant for the primary control, but it's not constant. Actually, it reacts with a longer time scale, and this brings back the frequency to 50 hertz. Okay, so you have primary control and secondary control. And they are pretty proportional derivative control, both of them. So it's, in principle, it's quite simple, actually. And that's it. And that's the, well, there are other levels of controls that we don't care now. Okay, there is a tertiary control to keep the enough secondary powers, enough power from the secondary control. And then there is also time control, and is that actually the 50 hertz of the power line of the electric system is like a clock. So actually there are clocks that work with that frequency. So, but it's a very bad clock because 50 hertz is a very low frequency. So it actually deviates. And what the operator does is every now and then synchronize the power grid with an atomic clock. Okay, so that's a reliable time actually. It's not relevant for this talk. So we only are concerned with primary and secondary control, just to keep the frequency in a good range. Yeah, follow? Well, to have this control, actually, you need power plants which are not producing, are idle. Okay, so you have to have some infrastructure just to compensate for the fluctuations of the frequency. Okay, so they stop. Sometimes the demand increases. You bring those online, and you need that to compensate for that consumption. Okay, and this is a very expensive thing because you have machines that have to be available but not producing. Okay, and these have to be paid for. And in Spain, this is called pagos por capacidad, and it's actually a large amount. It was in the last 10 years. It was 7,000 million euros. This goes to the utility companies that have these machines. Okay, so that's something expensive. So the control is something expensive. You would like to avoid that. Okay, but since the demand is fluctuating, you need that control. Okay, just keep this in mind. It will, as we go, it will make more sense. Okay, so this is the complete model for the power plant. So we have the swing equation, which is the variations of the frequency with the difference of the mechanical and electrical power, and then you have the primary control, secondary control, okay, and then we need a model for the electric demand, okay, that is fluctuating in time, okay, and this electric demand we put three terms. We have a constant average demand, okay, so the demand never goes below a certain value, so you have an average, okay, which is constant, and then you have a fluctuating part, which is the one that we will have to model somehow. That has also two parts. Well, this is not, it has here one plus, it has a part which is part of the consumption which is frequency sensitive, okay. So I mean, for instance, something which is resistance, the power of resistance does not depend on the frequency, okay. So it's this one here. But there are some machines, in particular synchronous motors, machines which are rotating, that rotate in synchrony with the frequency. And when the frequency changes, its power changes also. So the power depends on the frequency, okay? And this is this part here, which is actually a small amount. I think is less than 8% or something like that, okay? But nevertheless, we keep it. It's like a damping, okay? So these machines, if the frequency goes down, consume less. And if the frequency increase, consume more. Okay, so that's the easy part. And now we have this load here, which is time dependent, which is us switching on devices all the time, okay? Essentially stochastically. So how do we model that? No? So the next thing we have to do, before that, this is just the response of the power plant to an increase of demand. So have a look here. So this is 50 Hertz, okay? So machine is working constant speed, constant load, and everything is at a stationary point. So you have frequency of 50 Hertz. Here at a minute, certain point here, you increase the demand a lot, well, about 10%, okay? What happens then when you increase the demand? This breaks the machine, frequency goes down. So you have a large drop, and then when the frequency goes down, the primary control stops this fall, okay? Essentially increases the mechanical power to stop this drop. And this is stabilized at a new frequency around 49.993, whatever, okay? This response takes just a few seconds, 10 seconds, 20 seconds, the frequency is stabilized. And then, at a larger time scale of order of minutes, 10 minutes, or 8 minutes, or 10 minutes, the secondary control brings more power online, okay? Accelerates again the system, and brings the frequency back to 50 Hertz, okay? So this is a typical response of a power plant, which is realistic. So this is actually like that. Okay, so this is actually like a real power plant works. So the model is a good description of the dynamics of a power plant. So before going to the demand, the frequency is the key issue here. So you want to have the frequency at 50 Hertz. Okay, and the frequency is a proxy of the balance between production and consumption. So if production is larger, frequency increases. If production is lower than consumption, frequency decreases. So all the system, all the control goes around the frequency. So you monitor the frequency, and then you respond accordingly. And that's what the primary and secondary control does. And so simply like that. Okay, so now we need to put the stochastic model for the demand. We need to put the stochastic model for the demand. Okay, so that's what I just explained. So the demand side, and this is actual real data, this is how the demand fluctuates along a day. Well, this is along a week. Okay, so this, you see the daily variation. So at night there is less consumption, at day there is more consumption, and here you can see also the weekly pattern. No? So weekdays and weekends. In this talk we are not going to talk about daily variations. Okay, we are concerned about, so this is intraday. We are more concerned here with the fast variations within the hour. Okay, so that's what I'll talk about here. No? So you see that this is fluctuating actually, fluctuating fast within the hour. Okay, so this is within the day, and this is within the day, and this is within an hour. Okay, this is just 2 hours. No, so for 9, 10, 10, 11, and you see how the demand is fluctuating all the time, and this is us switching on and off devices. Okay, So you see, and that's what I'm trying to model. So I will not consider daily variation. I'll put the average constant along the day, okay, just to simplify. And I want to model these variations of the demand. These are fast variations. Well, this is the demand variation. Okay, this is data from the UK National Grid Company, and since the demand is fluctuating, the frequency is fluctuating. Okay, and this is how the variation of the frequency looks. Because so you see, this is 50 Hertz. Okay, here, and this is along the day. This is the demand, and this is what the frequency does. Because we are switching on devices, so that you are breaking and then the power plant accelerates, and then you switch off and it accelerates too much. Okay, and this is fluctuating all the time. This looks like that. And this the system operator has the legal obligation to keep this within a range, which is actually 50.2, 49.8. Okay, so this is actually here. This fluctuation is already out of what they are by law forced to keep in control. To keep this under control means that you have to have a lot of reserves, and that's very expensive. So here there is a payback. About the okay, so that's what we want to control. That's what we want to model first. Well, these are more frequency variations. That was UK. This is the whole Europe network. Okay, this is along. This is within a day, within the hour, and this is in seconds. Okay, how the thing is variating all the time. And these are some measures we did here. Well, in our building at the IFISC, okay, we built a device that you plug it in the wall and measure the frequency. Okay, and you can see how these are the frequency variations in Palma. Okay, this is 50, 50.1, and this is fluctuating. Okay, we'll use this later. Okay, so how you model this? This is very complicated. A lot of type of devices, a lot of different profiles of users, and you can complicate this as much as you want. We don't want to do that, because as physicists, what we want is the simplest possible model, okay, to reproduce the frequency fluctuations. So that's what we try to do. And the simplest model we came up with is really simple. It's just you have a number of devices. So you have, well, in principle, you can divide them in houses or in groups, but you have L devices. Sorry, M groups with N devices. And each device has two states, on or off. Okay? You could put more different powers, no? But it's 0 or so on or off. Then we put all devices all called same power. You could also put some diversity in the devices. We put all the same. And then the model is that each device will switch on or off with a rate P or Q. So with rate P, devices that are off switch on. And with rate Q, devices that are on switch off. And that's it. So that's the model. It's that simple. And then the total power, PL as a function of time, is simply the sum of all the power of all the devices. PI that can be 0 or P0. And this is equal simply N is the number of devices which are on. Function of time, number of devices on times their power. That's the power consumption. So really simple model. Really simple model. As a matter of fact, this stochastic problem is well known. So this is the stochastic problem is N particles with two states, okay, and with a switching rate P and Q between these two states, okay. And this problem is you can solve it actually exactly, and this is done in the book. I made some propaganda here. This is the book of Raoul Toral and Pierre Collet, okay, about stochastic processes. And it's solved there exactly analytically. You can solve that. And you can actually write a Langevin equation for the number of devices on that has multiplicative noise with zero mean and data correlated. And if the two probabilities are the same, P and Q is the same, the number of devices on is half. Half of them are on, half of them are off in average. Okay, or you have some fluctuations. And the variance of these fluctuations goes as, well, the variance square goes as N divided by 4, the power of the device to the square. So this is the mean and the fluctuations of this stochastic. And this is the mean power, okay? And you can actually solve this for all times exactly. So N of T, you can solve it exactly. Okay, so that's simple. And devices that switch on and off stochastically. That's it. So is it good model? This is how it looks. So this is the demand. So the number of devices on, if you like. Okay, and you look how this looks. So this is switching on and off devices. Okay, you can see here at short time scales. You can see the individual switchings. Okay, and this is switching on and off. Okay, and this is doing like this. Looks like a random walk actually. You know? So you have switch on is a step forward, switch off is a step backwards. No? And this is making sort of a random walk. So these are short time scales. At long time scales of hours, it looks like this, something very stochastic. Looks like white noise, more or less. As a matter of fact, if you make a very long time series of this stochastic process, and this is the power, the power spectrum. So you make the Fourier transform of such a series. It looks like this. Look at the yellow line, for instance. And as you see, if for long time scales, okay, for long time scales, so you very long thing. So it means short, slow frequencies. The spectrum is flat. Okay, more or less, you see. This is typical of a white noise, no? A flat spectrum. It's something which is fluctuating a lot in the long time scales. Okay, which is okay. But in the short time scales, so large frequencies, short time scales, this decays with a power law with a slope -2. And this is characteristic of a random walk. Okay, so actually, yeah. So this stochastic process is like that. So for short time scales, is a random walk. Device switch on and off. Okay, a true random walk, the variance grow indefinitely in time. Okay, so you can get as much separated from the mean, no? As you wait. So the variance grows in a random walk. Here, since you have n devices, you cannot grow indefinitely. When many devices are on, you cannot keep growing. No? So it's a random walk is truncated, okay, and give this characteristic. It's okay. So that's how this stochastic process is. So keep this in mind. Well, and then this crossover between the, say, which is the white noise and the random walk, this crossover depends on the switching rate P. Here P is equal to Q. You give the average constant. Okay? So you change P. This crossover between the frequency, which is the crossover between the two regimes, let's say, moves. I think is the larger the P, this move, the faster the rate, this move to the right, okay? And otherwise goes to the left. Okay, excellent. So this is the demand model, stochastic, very simple. You need to put it in the power plant model to see how the frequency respond to this. Okay, so what we do is we put this simple model in the swing equation and the control, so primary control, secondary control, swing equation, and we introduce this stochastic demand in the model and see what happens to the frequency. And the frequency does something like this. So this is the frequency. This for two different values of P. For a small P, fluctuates little, so that you have few switchings per time. No? So these have less fluctuations. And this is the power spectrum of this time series of the frequency. Okay? And this for larger P, this fluctuates much more, and the power spectrum looks like this. The power spectrum reproduced is similar to what I just showed. No? So it has this slope here, more or less -2 of a random walk, and a flat thing. Okay? Okay, so you can see here this goes down, characteristic of a random walk, and here more or less you have a plateau, which is for low time scales, for long time scales, for low frequencies, you have more or less flat, and a crossover at a certain frequency. Correct? And if you change P, this crossover here, they say this characteristic frequency where the regime changes move to the left for a slower P. Okay? So we have a single parameter that changes this thing in the power spectrum. So what we did to see if this was a good model or not, what we did is now, look at this. This here is the frequency. This is the real data that we took from a plug in our building. Okay? So these are real frequency fluctuations. Okay, and when you make the power spectrum of the real frequency fluctuations look like this, which is very good. It's very similar. And from this real data, you can calibrate, you see the plateau more or less, and then the drop. You can calibrate this characteristic frequency where you have the change of regime. And this allows us, in our model, to choose the P, the switching rate, that reproduce more or less the real values. Okay? So such simple model more or less reproduces statistical properties of the real frequency fluctuations. which is excellent for us because now we have a model, very simple, and we can study things on top of that. Okay, and that's the value we choose. Okay, so this is for that specific value. This is how the model looks like. Okay, that's pretty good. And the power spectrum is well, yeah, more or less the same. Correct? So at this point we have a model for the power plant, and we have the model for the demand that works, reproduces real data. Okay, so now we can play with it. Okay? And what's what we run and have to hurry? Well, I say we use here P equal Q, so constant demand along the day. You can also put that P and Q are different. You can put daily variations in this model. We have not done this extensively. Okay, but if you change P and Q along the day, you can reproduce the daily variations. Okay, notice that during the day there are more fluctuations because there are more devices on, and the fluctuations go as the square root of n. Okay, so more devices, more fluctuations, less devices, less fluctuations. Okay, and that will be something else. I'm not going into that. Okay, so back to our problem of controlling the system. So you have demand and production. We have to match this all the time. Okay, and that's what is difficult because you need these reserves. And the idea, however, is that nowadays most of the power comes from fossil fuels. From fossil fuels. So essentially, this is a primary energy consumption in the world up to 2014. 88% is non-renewable: gas, oil, and coal. Okay, and we want to change that. No? So we want to change the power system in general, no? And we want to go massively to renewables to avoid CO2 emissions and so on and so on. What happens if you go to renewable resources? This here is the actual production of a wind farm. Okay, of a wind power plant. You see this fluctuates huge from day to day, even from hour to hour or from minute to minute. The renewables, the sun and the wind, are fluctuating a lot. Okay. So in addition to the fluctuations of the users, we have now also huge fluctuations in the production side if we want to integrate large amounts of renewables in the system. Okay. So you have a real problem here with the control. Because the power plants, which are the ones that are supposed to control, are now actually fluctuating also. Okay, so deal with that is complicated. Okay, you will need huge reserves because when the wind goes down, you have to switch on a machine that produces all that, all the time changing. So that's a problem. Okay, and that's why somehow we need to change the control procedure. And this is what is called demand side management. So instead of putting the control in the power plants, we have to put the control somehow in the users. So the users have to adapt to the available energy. And that's an interesting problem. That's what we do. Okay, and yeah, as I said before, that this was not a complex system because the users do not interact. If we have to introduce demand side management, okay, maybe the point is that we have to coordinate our switchings to avoid fluctuations. So at that point, we have to exchange information and interact in our, user profiles to make things better. At that point is where we make this system really complex. Okay, now we have really a socio-technical problem from the user point of view. No? So that's the thing. No? So instead of that, that's the normal thing. No? That the power plants, program all the production along the day, to follow the demand and so on. Here is us, the users. We have to use the energy when it's available. And when it's not, we have to save the energy, and then to reduce the fluctuations. There are several ways of doing that. Okay. Well, the first, of course, is energy efficiency. So if we use less, we will reduce fluctuations. That's how usually. Then there are programs which are called demand response, which are you have incentives to reduce, flatten, or shift the peaks of demand. Okay. If the electricity is more expensive at certain hours, you will try to not use it at that hours and use it later, no? And when you do it down, you can shift some consumption patterns, okay? Or even you can pay, is there called some industrial process that you can pay them money in order for them to accept orders from the operator to switch off the process, no? And save energy in peak, if there are peak demands, things like that, no? So this is called demand response. This is still top-down, so it's the operator that tells you when to switch on or off, okay? We are not going to start that. We are going to start something which is called dynamic demand control. dynamic demand control. And dynamic demand control is, in principle, is a technology, essentially, well, is a low-cost technology that there are some appliances, some group of electrical appliances that can decide to switch on or off depending on the frequency of the system. So the devices monitor the frequency. If a device has to switch on, but the frequency is very low, means that there is little energy available, then do not switch on and delay the switch on. And therefore, this device follows, let's say, helps to balance production and consumption. Okay, so this is a smart, what is called dynamic demand control. Okay, and this, for instance, in this paper in 2007, they proposed, the authors proposed to do this with fridges, for instance. So a normal fridge has to keep the temperature between 4 and 5 degrees. If the temperature within the fridge goes above 5, switch on, right? And then it cools down, and when it goes below 4, switch off. And when it is in the middle, it's a stop. So that's how a fridge works. So what they propose is, okay, so let's put the thermostat, instead of having constant thresholds, we can put that the threshold depends on the frequency of the system. Okay, so you monitor the frequency. And if the frequency is higher, you want to keep the device on. So the fridge keeps on, just not with, here in this case, for instance, it cools down till 3. Okay? And it's fine. It's still okay. So, and so if there is a lot of energy available, the fridges are storing that energy in the shape of cold. So you keep your fridge colder than usual, but this is keeping energy, so that later, since you have it's cooler, you can wait longer to switch on again, right? And the other way around, if the frequency is low, you keep the device off later, until 6 degrees. And this is still safe for the food and for conservation, okay? But this helps to regulate the so this is an example of dynamic demand control, okay? And well, this is the power consumption, and these are frequency fluctuations. Here you see without the control is the largest spikes, and when you have this control, they have 8 million fridges or something like that. They make a simulation. The fluctuations are, you see this peak here. With control is smoothed out, okay? Because the devices help to control that, okay? So essentially, all devices, millions of devices collectively, act as a reserve power. So you do not need to put these reserve machines now because the fridges are doing that to a certain extent. Okay, and well, an estimation is that how is that here? 40 million fridges is worth 80 million pounds per year in what would cost to have a machine to do that. Okay, so you save money. Well, it's 2 pounds per fridge per year. Okay, so you as user don't save a lot. But the system globally, well, saves resources quite a lot. Okay, so that's the idea behind dynamic demand control. Okay, I think I need to speed up a little bit to go to the point. This is the same with, instead of a fridge, this is with smart charging technologies. So this is a laptop that charges only when the frequency is above 50, for instance. Okay, a laptop is not much power, but you could do this with electric cars, for instance. Electric vehicles have huge power, large batteries, you could do the same thing. So when the frequency is down, it switches off, and when the frequency is up, it charges. And this is the state of the battery along the day. It's always, that's one is full charge, and never goes below 50%. Okay. For instance, here, the frequency is low. You see, it's below 50. It discharges because it's using batteries. Okay, but then when frequency recovers, it starts to charge again. Okay, so this also would help to keep the frequency under control. Okay, so now we have a complex system. No? So the devices see each other, in this case not directly, through the frequency. Okay, because if a device switch on, frequency goes down, the next device, the action will depend on the others. No? So we have interaction here, and emerging collective behavior may emerge. No? And in particular, one of the problems it may happen is that you may have oscillations. That if the frequency, devices switch off, no? And then the frequency is good, all devices switch on, right? And this makes the frequency go down, all devices switch off, okay? And you have a feedback here, and you get an oscillation, okay? And this may happen. This is what is happening here. For instance, this is because a fridge is actually an oscillator. Fridges switch on, then switch off, on, and it has this is the period, or this is the temperature, or is it temperature here. No, what is it? I don't know what. Yeah. So switch on, frequency goes down. Switch off, frequency goes up, no, and you have an oscillation. So through this mechanism of interaction, you may get these things to synchronize and get these huge oscillations. Okay. So you have to avoid that. To avoid that, actually, simple in principle is enough to make the switching random. When the device has to switch, you do it with certain probability. This spreads out the switchings, and this avoids this phenomenon. More or less. Okay. So the last 5 minutes, I have still 5 or 10 minutes. Pero? Yeah. Okay. So what we do here now, we want to introduce this dynamic demand control. And again, we need a model for that, and we do the simplest we can. Okay. So we do something which is device independent, and simply what we do is in our model, previous one. So you have, each device can be on and off, have the same power, and each device switch on with probability P or switch off with probability Q. Okay? So what we do is when a device has to switch on, for instance, with a certain probability, now a device has to switch on. No? Now it has to. Then you first check the frequency. If the frequency is good, it means that if the frequency, to switch on? Exactly. So if the frequency is low, is smaller than a lower threshold, you don't switch on. You stay off. Okay? You want to switch on, but there is not enough energy, don't switch on. Wait. Okay? If the frequency is larger than that threshold, means there is enough energy in the system, then you switch on. Okay? And in particular, is this epsilon. So we put, let's say, this range between plus epsilon and minus epsilon. Here in the middle, devices can switch on. Okay? Actually, above this line can switch on, and below this line can switch off. Okay? Out of these thresholds, the devices wait. Okay? To help to control the frequency. Okay? So that's the same, vice versa for the switch off. What happens when you do that? That's fine that this helps to control, but then the device is not doing what it's supposed to do. For instance, a fridge should be cooling, and it's not cooling. No? So at some point, you will have to cool later. Okay? And then this pending task, that's what we call pending task, will be recovered later when the frequency is good. Okay? And for that, we have a second threshold we call epsilon 1. So if the recovery of pending task requires the device to switch on, we do that only if the frequency is above omega 1. So if the frequency is above this second threshold, omega 1, that means there is a lot of energy now available, so we can recover the pending task that had to switch on. Okay? And vice versa for the ones that have to switch on. You follow? So we have this. So the demand control has two parameters. One, tolerance, epsilon, where within here you don't control, and above this threshold you control, and a second threshold for recovery depending task that you have been setting. That's it, that's simple. Okay, so with this, we can model, let's say, this complex system. So on how it works. Well, it works well in principle. Well, that's what I want to show you. So here is we apply the control without recovery pending task. We now put the second threshold for recovery very high, so that we never recover. Okay? So the devices, if the frequency is not good, they wait. Okay? And they may wait forever in this case. If this is so, the control is very good. Look, this is the frequency. Okay? Now the frequency is remember the threshold is for control is 50.05. Okay, just below the red line. The frequency is get very low. Okay, so the frequency fluctuations are within range. Okay. The problem is that you accumulate Q is the total number of pending tasks in units of energy. So along time, the pending tasks go up. Okay, because you control, you don't recover them, these go up. This is unrealistic. Okay, now this would not work. The fridge would get too hot at a certain point. Okay, so you need to include here the recovery of the pending task. Okay, and now here you have a payoff. Okay, because you have to decide where to put this threshold for the epsilon 1, the threshold for recovery depending task. Okay, and this is critical. Because again, if you put it very high, epsilon, so this is the frequency, this is the variance of the fluctuations, and this is the total amount of pending task. Yeah, exactly. So if this threshold, epsilon 1, is very high, means that you never recover pending task. The pending task is very high. Actually, this plateau is a finite time effect. Okay? If you keep integrating longer and longer, this actually diverges. So the pending tasks keep accumulating. So you have to reduce epsilon 1 so that at certain point, the system gets above, and you recover that pending task. Okay? So, for instance, you put it here. No? When you do this, actually the frequency fluctuations reduce because the recovery of pending times helps you. Because when there is a lot of energy, you recover pending tasks. This helps you to reduce frequency fluctuations. What's the problem? That when you recover this pending task, even if you do it randomly, you spread out the switchings, you get these huge peaks. Okay? So, let's say the system accumulates pending tasks. At a certain point, the frequency is good. These devices start to switch on. Okay? And this creates you trouble. Okay? Because the control cannot follow, the control of the power plant, and this creates your spikes. Okay? So you recover too much, you get too many spikes. If you recover too low, it's okay, but then you accumulate pending tasks, and you have to find here a compromise. Okay? We find that the compromise, more or less, it was good around 0.06 here. So the pending tasks are low, the frequency fluctuations are good, and I think is the final plot. Is this plot here? You see there are not many spikes. So it's good, it works. Okay, fine, excellent. So that's our result. It's good. We are happy. We still have a problem though. And this is how it looks now. This is, blue is without control. Now you put the dynamic demand control, and the frequency is in green. No? Clearly, you have reduced fluctuations. So the system works much better. Okay, so we're happy, but we still have. You can see here some green here. Okay, yeah? You still have some peaks. You can never get rid of these, let's say, rare events. Sometimes, stochastically, it happens that when you recover, many devices switch on together, and you have a frequency peak, and that's not good. Because it's actually large, and this can actually, we want to avoid that. So, and as a matter of fact, this is the problem. It's a problem. Here I'm plotting this is the cumulative probability of having a frequency fluctuation larger than delta omega. The stochastic case is the black line. Okay? So this means that, let's say, to have this is in log scale, okay? So to have a frequency fluctuation larger than 0, you have probability 1. Okay? But to have a frequency fluctuation larger than 0.15, you have this value here. But larger, for instance, you see that in the stochastic case, without control, you never have fluctuations larger than 0.2. Okay? The law is such that you don't have that large fluctuation. The probability is very low. This decays faster than exponential. When you put control, okay, and the yellow line is the case without recovery pending task. If you do not recover pending task, the probability of getting fluctuation larger than some value decreases a lot. Okay? Actually, the yellow line is very good, but you are accumulating too many pending tasks. Then when you put the recovery, you get these lines here. This depends on the value of the threshold epsilon 1. So if the epsilon 1 is too large, you see, so you reduce the small or medium-sized frequency fluctuations, but you get larger fluctuations that you hadn't before. Right? Before you didn't have these large fluctuations, and now you have them, because the probability distribution gets exponential tails. Okay, so you put the control, it works, but you have this drawback. And even if you tune the value, we choose the 0.06, which is the gray line, so you have reduced the fluctuations quite a lot. Still, because of this exponential tail, you cannot get rid of these rare events. So large frequency fluctuations, because stochastically, dynamic switch on to recover pending tasks, devices switch on to recover pending tasks, and create you this frequency peak. Okay, and this is harmful for the system. This is how it looks. Okay, so even for 0.6, you have these things here that bother us. Okay, okay. So and there's just 2 minutes to get rid of that. We did this one more step in this system, and till now we introduced this interaction. Okay, it was through the frequency. So devices were seeing each other through this global quantity that is the frequency. Now we have made a step further to make the system even more smarter. And what we have done is to include communication between devices. So device-device communication directly now. So they are interchanging information. This, for instance, within a house, okay? So they can directly through your Wi-Fi network or whatever, okay? Such that if a device has to switch on and the frequency is not good, it cannot switch on, it checks if other device in the group has switched off before, within a certain time window. If this happens, we allow this device to switch on. Okay? So we do this such that this is not helping to control the frequency, but helps to keep the consumption of a house constant. Okay? Because if this has to switch on, waits until when this switch off, this switch on, and the total power keeps constant. Okay? So this is not helping to control the frequency, but it reduces fluctuations. And then the power plant will adapt, the control of the power plant will adapt to that amount. Okay? So that's what we have implemented. And you can do this within a house, or you can do it at different scales. You can do it, let's say, countrywide by internet communications, okay? Or you can use something which is called power line communication, that the devices can communicate through the cables of the grid, okay? So and these maybe, so they can send a signal in the power lines, and the signal can travel before it dissipates, let's say 1 kilometer. No? So within 1 kilometer, you can synchronize devices, the switching of the devices, okay? So this makes the system really complex. So we have checked this, and we have implemented this thing I just told you. So we allow for these switchings, if you interchange the switch on a device if another switch off within a certain time window. And this worked well. This is the previous case, okay, I just explained you. And now here we have included this device communication. And this works very well now, okay? This works very well. And I will not extend much. So this is the black is the random case. And now including the device-device communications, the 0.6 is this thing here. You really have you really avoid desynchronization for recovering pending tasks now, okay? Because you allow these switchings, no? And this is much more efficient in keeping the total power constant and reducing the fluctuations. Okay? And if you compare, and this is I think is very illustrative. So this is the demand, and these are frequency fluctuations. And these are pending task. The top case is the chaotic case, is no control. So this is the demand with no control, and this is the frequency fluctuation. So you have large frequency fluctuations. You apply dynamic demand control without communication. It works okay, but you still have these large peaks, which is these rare events, no? Because of the recovery pending task. And then when we put this device-device communication, this looks much better now. Well, you see, here, this resembles more this one than this one, okay? So actually the control is more subtle. It acts less times. But when it acts, it works better. And looks here, the frequency now is always within ranges. You never have this synchronization effect where several devices switch on simultaneously. No? So this is working very well, okay? And as a matter of fact, this is the pending task in this case is around 8. The same case with these device-device communications, pending tasks are reduced 10 times. Okay, so actually the system works very well in this case. So it's a nice example of let's say how a complex system can self-organize for a proposed task of keeping control of the fluctuations. Well, yeah, just we are done. Okay, you don't need all the. What I've done now is all the devices were smart, okay? Which we have checked that only if you put just 20 or 30% of the load smart, is enough to already have a good effect, okay? So you don't need to have all the devices smart, because you can. A TV has to switch on when you want. So it works with the 20 or 30%, it works, okay? Well, and that's it. So the conclusion is that we have to go. We want to remove fossil fuels. Fossil fuels, we need to introduce renewables. We have huge fluctuations. We need to spread to distribute the control of the system among the users. So we have addressed this issue. Okay. You also distribute the production with solar panels and so on. But for the control, a way to do it is to put this dynamic demand control, okay, which is good. And we have shown that. Well, we have proposed a model that reproduce these characteristics, the characteristics of the real frequency fluctuations. We have shown that DDC works to a certain extent, but when you introduce interaction among the plane, it works very well, okay? And essentially, 30% of the total devices being smart will be enough to keep things under control with a large integration of renewables, okay? So that's the take-home message. And yeah, so thank you all for your attention.
I would say less realistic, but it's assuming that all devices have the same consumption. How would that change? Because we know that the iron has a large consumption, but probably the fridge not that much. So how could you include this into the model?
Yeah, that's a very good question. We have tried to explore that a little bit, but we didn't do much. In the model, we're very simple, simply. So you have these 1,000 devices. You can put, instead of 1,000, you can put 1,000,000 devices and different powers for all the devices, okay? We don't expect a big difference. Essentially, as a matter of fact, the statistical properties depend only on the, let's say, the product NP. That total amount is what globally the statistical property depends on that. So you put different powers and the different number of devices. I think in the large picture would not change. And we put some diversity in the consumer, and we don't see anything special. So the things work more or less. So I don't expect that to be a critical thing. So, but isn't, well, yeah, we should look at it in more detail.
Any other question?
So how do you think it would compare to the approach of, say, in the future we might be able to build big batteries like with Tesla or something? How do you think it would compare to that approach? I mean, do you think this would change? I mean, that would essentially solve this problem, or do you think you would still need something like that?
Oh, well, so the batteries go in the same direction, so that's very good. A battery would work as this. No? So the battery would work exactly the same as what I've just explained. Simply because the battery, what we'll do is if there is too much, so the frequency is too high, we'll store energy, and if the frequency is low, we'll deliver energy. No? So it actually will be, it's in the same model, no? Okay? So it will be actually the same. So but you can avoid, let's say, is doing the same thing. Some devices, so some smart devices, a number of them is equivalent to a battery of a certain size. And if you compare the values, actually in that that we did in that paper, this is very slow. So I'm trying to do it that the fridges, these 20 million fridges, that's a lot of energy. So that's a hell of a battery. You understand? So I think everything would complement because we need probably everything. So you should integrate the batteries if you have them, and the smart devices to also to compensate for that. And I want to see the number because in that I don't know. This is very low. Well, if I get that, I don't know. Remember, it was. I don't remember how many megawatts. So that's the hell of a battery, okay? So, but having a battery at home could help. Nevertheless, batteries are expensive, because batteries are very expensive and have a lifetime. Okay, maybe in 10 years, the battery you have to replace it. Okay, and maybe a fridge or a boiler, electric boiler, maybe it will last 20, 25 years. Okay, and will do the job as well. Okay, so you need everything. You should integrate everything. So I don't think batteries alone will do it.
More questions? Okay, so if not, we thank Damià again and we'll go for the coffee break.